we arrived at this nice expression for the partial differential scattering cross-section, and I wrote my potential as the sum of many little potentials like that. And I want to put this into the expression, and I want to carry out the integration over the I'll carry out the matrix element calculation for the Neutron part of the bracket. So that means that I'll be converting this into a plane wave state, and then I'll be carrying out this R integration. I won't touch the bracket associated with the sample condition. That'll remain intact. Okay, so let me just show you what the expression then looks like. I'll do that in the middle board here. Okay, so I think I'll just out. Okay, so I'll have my expression again: d sigma, d omega, d e prime, and most of it stays the same. And I think I'll later try to simplify matters. Now, the prefactor is modified slightly because of the nature of the plane wave state of the neutron. So that's showing up is a 1 over 2 pi raised to the minus 3/2 power for each of those. And that ends up shifting the 4 pi squared to the denominator. So now what we get is actually a m divided by 2 pi h bar squared, and that thing is squared. That's just the numerical prefactors. I still am summing over L and L prime, lambda and lambda prime. For my initial and final neutron state, I'm still averaging over my thermodynamic average. And now, however, my matrix element only involves the state of the sample. That's the final state of the sample. And then I'm going to have to sum. I'm going to have to sum of all of the copies that I have of this unit cell interaction potential. And showing up as well is going to be an e to the I q dot RL. Okay, so that thing shows up as we carry out our matrix element calculation for the neutron part of the wave function. This will be, I should probably use a capital Q. That's the momentum transfer, k minus k prime, and this is the position of the scattering potential in a unit cell that we've labeled by RL. And then also showing up will be the Fourier transform of the individual interaction potential. And then finally, I close my bracket, and I do have mod squared. And I hope the view is wide enough so that you can also see energy conservation, which we need to still have in there. And I don't need to repeat what was in there. That did not change. Now, what did show up here was a Fourier transformed interaction potential. And I just want to remind you what that looks like. BL of Q is going to be integral d3R, so integral over all space of VL of R as such. Okay. Now, exponential. My Fourier transform of the interaction potential. And as we progress, you'll see that in the case of the strong nuclear force and nuclear scattering, then you'll find that all of this just becomes the scattering length. That's all. There'll just be a B that comes from this. In the case of magnetic scattering, which we'll talk about somewhat later, then this actually will essentially become the spin operator multiplied by the form factor. So this one takes a more important role when we talk about magnetic scattering. So that'll be the next, I think, next week's lecture. So this is VL of Q. Good. So now, let's see where we can now progress with this. Basically, I would like to develop this expression, and I would like to actually, there are a couple of things I'd like to accomplish. I would like to be able to sum over all of the final neutron states, lambda prime. And this I would like to do using the completeness theorem, which says that 1 is equals to sum lambda prime, lambda prime. So I'd like to employ this expression. So this means that I'll have to basically develop this modulus squared. And then I'd like to finally carry out that summation. Now, I'm going to have some troubles with that, because inside of this Dirac delta function, just to remind you, I have h bar omega minus e lambda prime minus e lambda. Oh. Okay, so lambda prime shows up in there. So I will not be able to just trivially carry out the summation. So what I have to do is to basically incorporate this delta function into this matrix element, essentially, is what's going to happen. And there'll be a couple of steps that I need to undertake in doing that. And the first step will be to replace the delta function by a time integral. So I'm going to write delta function of h bar omega. That has dimension of 1 over energy. That is equals to 1 over 2 pi h bar integral e to the minus I omega t dt. So this is how I'd like to express this delta function. And then I'm going to, I think I'll just give you kind of various, we were kind of a little short with the time, so I want to give you various steps, and then I'll take the giant leap. So I will use that, and I'm also going to use the so-called Heisenberg representation of operators. And this will be as follows. So for my operators, I want to put those as time-dependent operators, e to the I h t over h bar, a e to the minus I h t over h bar. And if this goes a little fast, by the way, then I will be uploading my notes, so you'll be able to follow the whole thing. It's pretty straightforward, a little bit cumbersome, but I've found very valuable to really know each of these steps pretty well in thinking about experiments. So that's why I find it useful to tell you a bit about it. So these are basically the steps that I'm going to be employing to simplify that expression. And I think what I'm going to do is I will write down what the simplified form then looks like, so we don't get to do too many manipulations here on the screen, as it were. And so I want to write it in the following way. So let's see, can you focus over here? Okay, so now I'm going to write a nice simple form for this partial differential scattering cross-section, and we'll take note of each of the terms that will show up. So these things were well known to you, previous expressions. Then I have now a double summation over position coordinates, and I have a time integration e to the minus I omega t dt that shows up. So all of this, if you will, is sort of fluff. It is important, but we're not gone really to the core of the expression yet. We have a double summation and we have a time integral showing up. And then what's going to show up, which is the most important part, is a so-called two-point correlation function. And let me write it, and then we'll talk about it. IQ dotted with RL times 0, VL adjoint Q Q comma 0, and then V L prime Q comma T, and then e to the I Q dot R L of time. So that is the expression in all its beauty or horror as you wish. So this, what I mean now by this bracket is the following expression. Let me just make that clear. So this is a thermal expectation value of some sort of operator that operates on the sample state. What I mean by that is that this is summation over lambda, all states of the sample, probability in thermodynamic equilibrium of occupying that particular state, and then expectation value of that operator in that particular state. Now, let's just dwell a little bit on how this expression came about. And you should feel free to ask questions if there's something that's unclear. First of all, it becomes a double summation over position coordinates because of, can this be seen on the screen? No. Oh, okay, maybe that becomes too much to do. So maybe just focus over here. So it does become a double summation because of taking the mod squared of the matrix element. And each of the operators had a summation of L, so I've got to keep track separately of those two summations. I have the time integral here because I ended up replacing my Dirac delta function by this kind of time integral. Now you could say in my Dirac delta function, I had h by omega minus a difference in energy of the sample. Where did that all go? Where did all this, where did the, in the Dirac delta function, where did the terms that had to do with the change of the sample energy, where did they go? Where they went were into the Heisenberg representation of the operators. By using these time-dependent operators as we define them here, you will find if you were to replace those expressions into there, you'd find that when these time evolution operators act on the lambda and lambda prime states, they will develop exactly those phase factors that we needed in our expression for the delta function. So that's essentially where this time parameter came in. And then, of course, we end up with a product of an operator and its adjoint because we were doing a modulus squared of a matrix element. And we have both a Fourier transformed potential operator and this particular phase factor, which came about because we are repeating this potential at many different places in space. And so that's where we pick up that particular type of phase factor. So that's sort of in brief terms how this showed up. Now I want to point out that you could, as well as using the path that I chose in getting to this expression, you could also derive this essentially from time-dependent first-order perturbation theory. So if you calculate the rate of transition in first-order perturbation theory, then you'll know that that also has to do with a expectation values squared of this operator. So I'll be able to, and this particular expression from time-dependent first-order perturbation theory is also sometimes called Fermi's golden rule. So many books will just jump into the problem at that point, and that's perfectly fine. We took a slightly different path because we like to think about the geometry of the scattering process. And so we started off talking about the simple elastic potential scattering and developing the Green's function for the Neutron propagator, etc. And eventually got at the same expression once implementing the Born approximation. So all of these things eventually generate the same expression for this scattering cross-section. Good. So this is actually a good step to have arrived at. And now we would like to try to actually use this expression in a slightly more specific case. Because remember, I didn't say anything about the nature of this interaction yet. So I can later dial this expression up when I want to talk about magnetic scattering, and then I'll start from this point. But what I'd like to do today, in the remaining 15 minutes, is try to think about the case of nuclear scattering from a harmonic crystal. And so this will be a very specific example of an interaction potential. And I'm going to go down here to develop that expression. I think I'll come all the way down. Yeah, so what's happened now is we are going to use the Fermi soda potential, and our expression for VL of Q. VL of Q, remember that was this Fourier transformed interaction potential. That is now simply going to be the Fourier transform of the Fermi soda potential. So that was IQ dot R. And then I'm going to get here a 2 pi h bar squared divided by m. And I have my scattering length. Let's take that as a real number in this case. And then I have my Dirac delta function, because I'm going to put this potential right at the origins. That's my potential. That's my Fourier transform. And I need to do integral over all space. So this one is particularly nice and simple for us to deal with, because that will just produce, by design in a sense, 2 pi h bar squared divided by m times b. So this one does not have any wave vector dependence, because the length scale associated with the strong nuclear force is very, very short, and in fact, so short that we neglect it in this calculation. We make it infinitely small. So there's no wave vector dependence from that. So this I can now pop into, I can pop it into my expression for the scattering cross-section. But I want to take one important step prior to doing that, because as we said when we were talking about inelastic scattering, we want to think about something a bit more interesting than a static sample. So we want to think about the case of the atoms actually being able to move about. And so these atoms are not going to be fixed at positions RL. They will have an average position, and then they'll be able to move away from that position in accordance with a harmonic potential. So it's a simple treatment of the harmonic crystal, which will now come into play. So it means that my position coordinates, which for an atom at position L, are now actually going to become time-dependent. These will now become time-dependent operators, because we're working in this in the language of these time-dependent operators. And we will have one term which is the average position that belongs to that atom. It has a certain place that it should spend most of its time, or which will be its average position. And then it has a displacement away from that, which I'm going to call UL of t. And so this will now be, if you will, a vector operator on the sample state. And everything will turn out to be pretty simple in the end, because it is a harmonic crystal. But in principle, I have to keep track of that. Good. So now I'll put that into my partial differential scattering cross-section, and I'll show you what it then looks like. Okay, so there's this guy stays around. All of this prefactor now cancels out, and I just get scattering length squared. And then I'm going to do, I have my time integral, and I have my double space summation LL prime, and then I have, let me just see here, L prime minus RL. This term, it's somewhere else over there on the board, but this term is a time-independent phase factor that comes about due to the displacements of the atoms through their average positions. So this one is actually not a very complicated term, but it's a very important term, obviously, in our expression, but it doesn't have any time dependence and doesn't show up in the matrix elements. And the two-point correlation function, which we advertised before, looks as follows. There's e to the minus I q dot UL0, e to the I q dot UL prime at time t. All right, so that's that is the entire expression. I have sort of simplified things to the case of a Bravais lattice at this point. So you'll see that in this type of measurement, so measuring the inelastic scattering associated with a strong nuclear force, it will be this type of two-point correlation function that will show up. Now, this this is not entirely a trivial matter to deal with, but I don't want to complicate our discussions too much. So I want to actually cut short a little bit the development of this thermal expectation of a two-point correlator in the following fashion. I want to say that once we're talking about a harmonic crystal, then there is actually a giant simplification that's possible for this type of thermal expectation value. And it will be described quite nicely in the book, which I'm actually using as I go through this. And that is, I'm using this book, which is Theory of Neutron Scattering from Condensed Matter by Stephen W. Lovesey. Oh, sorry about that. Just there you go. So you can see this in some of the material that's written, but this book has a lot of this information and much more in it, and it's a good reference work for you to look at, and it will describe how this two-point correlation function can be simplified. And let me just, if we go to the center board, I will just write down that particular simplification. Okay. So I'm going to just write that result out. So this thermal expectation value that I was talking about, this two-point correlation function, can be written as follows. E to the minus dot u squared thermal expectation value, and then exp of thermal expectation value of q dot ul of 0, q dot ul prime time t. And I do this and that. Okay, so what has happened here is that as a result of the harmonic nature of this crystal, we have been able to write the expectation value of the product of two exponential functions as the product of exponential functions of a thermodynamic equilibrium. So you'll notice that prior to this step, I had the expectation value of basically products of exponentials, and now I have the expectation values show up in the exponent of these functions. So this step is actually pretty straightforward once we have the harmonic approximation. Okay, now, so that's one step I need to take, and now I'm going to take an additional very, very important step, and I'd like to get to this today, in that I'm going to make the approximation that these displacements are relatively small on the scale of inverse wave vector, so that this dot product ends up being quite a small dimensionless number. Q dot u is a dimensionless number, so if my wave vector transfer is not too large and my displacements are not too large, then I'm going to be able to Taylor expand this whole thing. And then I can write this as being equal to e to the minus q dot u squared. And then this one Taylor expanded there'll be a 1, okay, plus, and then just this guy again, which is q dot ul 0 q dot ul prime at time t. And then there'll be a half times some sort of expectation value squared, etc., etc. This is called the multi-phonon expansion. This factor here is called the Debye-Waller factor. And then this term here will actually be associated with elastic scattering. This term will be associated with one phonon inelastic scattering. This term will be associated with two phonon inelastic scattering, etc. And so all of those terms are actually present when we go and look at the full inelastic scattering cross-section associated with a nuclear interaction. But in our way of thinking about the scattering and in the experiments that we design, we tend to emphasize these two terms predominantly, the elastic term and this one phonon inelastic term. And I think what I'd like to end with today is just to write down the cross-section that would come out from this term with the factor 1. And that actually is pretty pretty straightforward. I'm just going to write it down here. So d2 sigma d omega d prime equals 2. And so I'm just going to do what I would call the elastic part. Okay. So most of it we already had. There's a b squared. And let's see, then I have to dial myself up there. So let's see. So I have my. I think I'd like to just so 2 pi h bar integral e to the minus I omega t dt. That's my time integral, and then I have my summation L prime, and I have my famous phase factor that we I've become accustomed to. Okay, I previously mentioned that this one is a relatively simple term now. It does not have a dynamic nature to it. And then comes you guys on the screen don't see it so well, but this 2-point correlation function. Maybe we should just point over here briefly, if you could. I'm basically working from this expression. So this is this rather complicated 2-point correlation function involving exponential functions. And through the magic of the harmonic crystal approximation and then the multiphonon expansion, I was able to simplify that to this form. And of that, I'm only picking out this term 1 here. So that one is pretty simple. That is just actually a 1 that shows up. So I won't even write it. Right, so that's actually the expression that I have. Now, I forgot something very, very important, which was all that I was actually going to achieve from this, in a sense, which is this factor here, what I call the Debye-Waller factor. That one did show up in front of the 1s. That one has to be there somewhere in the expression, minus expectation value q dot u squared as such. Okay, now, at this point, we now notice that this time integral here, that just becomes a delta function in energy transfer. So I'm going to write that at the very end, delta function energy transfer. And because of that delta function, k and k prime have the same length. So that just becomes a 1. And so I just have my scattering length. And then I have my normal double summation over this type of phase factor, which we have already seen before. And we know that that's equals to a summation of all reciprocal lattice vectors, because only when wave vector transfer matches a reciprocal lattice vector can I get a finite value for that sum in a periodic system. So I'll get q minus tau, like that. So that's all of my normal stuff that we're familiar with. And then I have my Debye-Waller factor e to the minus expectation value of q dot u squared, and then my delta function. Let me spend a few minutes just summarizing what has changed compared to when we talked about the completely static crystal. So when we talked about elastic scattering and a completely static crystal, we had no possibility that the atom could stray away from its average position. It's just sitting exactly where it was supposed to be. And so this very, very small interaction potential was fundamentally what was scattering the neutrons. And in that case, we ended up with an expression which just looked like all of what's here. That was the expression we had previously. Okay, what's happened now are really two things. One is that we've attained this so-called Debye-Waller factor. Now, what does that do? It basically takes account of the thermal displacement of these atoms from their equilibrium position. And you'll see that its effect is to attenuate the strength of this Bragg scattering as we come to higher and higher momentum transfer. So in a sense, what's happened is that instead of being really the Dirac delta function Fermi-Soda potential, this has now been distributed somewhat in space as a result of the thermal motion and the quantum motion. So that is the quantum zero-point fluctuations will have the same effect, or they will have such an effect. They spread the apparent size of this interaction potential, and that causes the overall scattering intensity to decrease at higher and higher momentum transfer. So that was the appearance of that term. Now, The last term is also very, very important, and this relates in a sense to what Takeshi Igami was talking about in his first lecture. He talked about the surprising aspect of there actually being any elastic scattering at all when we interact with these materials. And in a sense, in this formalism, what we've seen is that the elastic scattering actually arises from time-independent parts of the two-point correlation function. So if you look at this expression, remember this entire expression came out when we, that is our multiphonal expansion of the two-point correlation function. And this part does depend on time. As time goes on, this part will actually completely vanish because we'll lose correlations between an atom and its displacement at position L as compared to an atom at site L prime at some very, very late time t. So this one actually dies out when time becomes very long. However, this one does not die out. And the appearance of this constant term ensures that this time integral produces a delta function of elastic scattering. So whenever you have in your two-point correlation function a time-independent part, so some sort of time-independent correlations, then in this formalism you produce elastic scattering. All right, so today we managed to sort of rederive, if you will, the elastic scattering cross-section, and we're ready in the next lecture to talk about inelastic scattering, which will be associated with this term in the multiphonal expansion. So thank you very much, and apologize for the connection problems. I hope some of it came across nonetheless.